तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so today let us look at a very important aspect of quantum mechanics which goes by the name of perturbation theory. The idea is the following: generally the class of problems or the class of Hamiltonians for which you can find the eigenvalues and the eigenfunctions explicitly is very small. Apart from a few well known examples like the hydrogen atom or the harmonic oscillator in any number of dimensions, the number of exactly solvable problems is very small. Just as in classical mechanics too, you realize that the number of exactly integrable problems was also very small. Most problems are not integrable. In exactly the same sense, most Hamiltonians in quantum mechanics cannot be analytically solved, in the sense that you can't write down eigenvalues and eigenfunctions explicitly for them. So several approximation methods have been evolved over ever since quantum mechanics began, as a matter of fact, with varying degrees of rigor and success, and today perturbation theory is a well established part of quantum mechanics, and what we are going to do here is to look at its rudiments, the very basic elements of a certain kind of perturbation theory. Now what I have in mind is a system whose Hamiltonian H can be written as the sum of two parts, and the first part is supposed to be the free or solvable Hamiltonian H naught, which we are going to assume is something for which you can find the eigenvalues and eigenstates explicitly, plus a small correction to it. Now of course one has to make some sense out of this word correction. Classically, if I wrote down the correction as some H prime, then one could say if H prime is numerically always small compared to H naught, this is a small correction to it, and so on. To keep track of how big this correction is, one introduces generally a parameter. So let me write parameter lambda, which is taken to be small. This is sufficiently small that lambda H prime serves as a correction to H naught. Now quantum mechanically H naught and H prime are operators, so the question of what you mean by small is not very clear immediately. Well, we can do it in two ways. Either I say that lambda is a parameter very close to 0, some real number which is very close to 0, and H naught and H prime are comparable to each other, that is one possibility. Or I say lambda, I set lambda equal to 1, and I say H prime is such that all its matrix elements are very small compared to H naught in some given basis. Now we are going to take the attitude that lambda is a small parameter, we will put it in explicitly because we would like to keep track of terms of first order, second order, third order, and so on, and they would refer to powers of lambda which appear. So this is a small parameter. And in this course we have restricted our attention to Hermitian Hamiltonians. So H naught is a Hermitian operator, H prime is also a Hermitian operator, and lambda is a real number. Okay, so the eigenvalues of H would continue to be real, which is what we want. Okay. Now how small H prime should be, what I mean by smallness of this term lambda H prime will become clear as we go along. Now of course you could also say, in general, the perturbation that you apply to an unperturbed system with Hamiltonian H naught could be time dependent. You could actually apply an electric field on a charged particle which has got some time dependence. So in general this is a time dependent Hamiltonian. This portion is time dependent and that makes H time dependent. Then the question of interest is the following: if H naught has energy levels of some kind, these are all the energy levels of H naught, then the moment you switch on H prime, it would cause transitions between these stationary states. And the question of physical interest is, given the system initially in some given eigenstate of H naught, what is the probability that it is going to jump to some other state under this perturbation? What is the probability per unit time? These are called transition rates or transition probabilities, and they will become relevant. Okay. On the other hand, you could also have situations where this is a simpler situation where H prime is not dependent explicitly on time, it is just a Hermitian operator, and we would like to ask, given the eigenvalues and eigenfunctions of H naught, can you find the eigenvalues and eigenfunctions of H naught plus lambda H prime? This. Now you appreciate the problem is totally trivial if H prime commutes with H naught. Then if you can diagonalize, you can simultaneously diagonalize two mutually commuting matrices and find a common set of eigenstates. Therefore there is no fun in it at all. On the other hand, if H prime does not commute with H naught, then non-trivial things can happen. Just to set this stage and show you what can happen, let us take a very simple example where H naught is a 2 by 2 matrix, and suppose H naught has two energy levels. So H naught is of this form. There are two energy levels, let me call E1, call them E1 and E2. I have already diagonalized H naught and written it in its eigenbasis so that you have two eigenvalues and the off diagonal elements are 0. Now it is easy to see that if H prime is another diagonal 2 by 2 matrix, then the eigenvalues are obvious, you write them down immediately. On the other hand, if H prime is not a diagonal matrix and does not commute with H naught, then you have to do a little bit of work. So suppose H is equal to H naught plus lambda times something or the other. So 0, let us put 1, 1, 0. This is the simplest sort of thing you could have, just two off diagonal elements. Okay. Then the question is, what are the new eigenvalues? Well, this is not hard to do because H now is E1 lambda lambda E2, and the task is to find the eigenvalues of this matrix, 2 by 2 matrix, which is not very hard to do, it is trivial to do this, but they clearly will not remain E1 and E2, they will have a certain function of lambda here in addition to the original eigenvalue. So what is this thing equal to? So lambda 1 comma 2 equal to, you have to solve the following secular equation. You have to solve lambda squared minus lambda times E1 plus E2 minus, oh I should not have used lambda, let us call this for the moment delta, some small number delta, so lambda times plus E1 E2 minus delta squared equal to 0. That is the secular equation which is going to give me the eigenvalues of H. And what are the roots here? This implies that the roots lambda 1 comma 2 are E1 plus E2 plus or minus square root of E1 plus E2 whole squared minus 4 times E1 E2 minus delta squared. So E1 plus E2 whole squared minus 4 E1 E2 is E1 minus E2 whole squared. So this is whole squared plus 4 delta squared divided by 2. Now of course to simplify it further, you have to tell me whether E1 is bigger than E2 or E1 is less than E2. Okay. Let us, without loss of generality, take E1 to be bigger than E2. Then this implies that lambda 1 comma 2, lambda 1 for instance is E1 plus E2 plus, I pull this out and it becomes E1 minus E2. So it is E1 plus E2 plus E1 minus E2 times 1 plus 4 delta squared over E1 minus E2 whole squared to the power of half, and you have 1/2 this whole thing. So 1 comma 2 is this plus or minus that. So what does lambda 1 become? Lambda 1 is E1 plus E2 plus sign here, so this is E1 minus E2, the E2 cancels, so you have E1 because this 2 cancels against 2 E1 there, plus this correction term, and this correction term if delta, so now we begin to see if delta much less than E1 minus E2, if this is permitted, if it is much less than this, then you can do a binomial expansion here, and then you get E1 plus the first term is 4 delta squared with a half there, so that is going to give me a half, 2 delta squared and cancels against this, so it is E1 plus delta squared over E1 minus E2 plus order delta to the power 4. It goes on to all powers. So the important lesson is that even though the parameter was linear in the Hamiltonian, this had just first order term in delta here. When you compute the eigenvalues, you have all powers of delta in general, not just the first order term but everything. And similarly lambda 2 is E2 because you want to choose the minus sign here, and then it will give you minus, again the same argument, delta squared over E1 minus E2 plus terms of order higher order, term of order delta 4 and so on. Okay. So what is the important lesson we learn? That even if the Hamiltonian has a parameter like lambda or delta and it is linear in delta, when you actually compute the eigenvalues, in general you expect an infinite series. There will be corrections to the eigenvalues of order delta, delta squared, delta cubed and so on. In this particular problem, the way it appeared, since the same delta appeared both places, only delta squared appears and therefore all the odd powers vanish, only the even powers of delta remain. But that is not true in general. It is clear that depending on the form of the Hamiltonian, you would have an infinite series in delta. Okay. Now that is the lesson we want to take over. Now in the 2 by 2 case the problem is completely trivial, because you give me a 2 by 2 matrix and I can diagonalize it, provided certain conditions are satisfied. I can find the eigenvalues always, there is no difficulty at all. But what happens in general? We would like to address this problem in general. First important thing to note, and this is going to help us understand when this is said to be small compared to that, is already sitting there. This perturbation here, which in this case was just delta here and a delta here, it is not sufficient that this delta is small compared to the two eigenvalues, original eigenvalues E1 and E2. So if you look at this matrix and say, the unperturbed is just these and these are the perturbations, so perhaps the perturbation can be, the corrections can be found in a power series as long as this number, the off diagonal elements, are small compared to the diagonal elements. That is not true. Okay. What is needed? What is the actual criterion here? It must be small compared to the energy differences. So it is not sufficient to say that it is small compared to the original eigenvalues, but it should be small compared to the differences in energy. Okay. Then it looks like we are in business and we can do perturbation in a power series. Okay. And the reason I emphasize this is because in general you are not going to be able to get an analytic formula like this. You see, once I have an explicit formula like this, I do not need perturbation theory, there it is, to all orders in delta. But in general, for more complicated problems, you will only be able to find things to a certain order, correct to certain order in this perturbation. And therefore we must be careful, find out when these series converge. So with this little toy model, let us look at the general problem. So yeah.
Lambda equal to E1 plus E2.
Lambda 1 plus lambda 2
Equal to E1 plus E2.
yes, yeah, this doesn't matter, that's simply because in this particular problem it was so extremely symmetrical, but it's not going to happen in general. You're going to have a large number of energy levels and each of them is going to shift by a certain amount and we want to find out by what amount. The other important lesson, other important crucial point is what he's already raised. What happens if E1 equal to E2? Then you have something totally different happening. This kind of expansion is not permitted at all. Then you have to do what's called degenerate perturbation theory. You have to now do the problem all over again and you can't do this kind of little trick here. So we are going to assume to start with that this perturbation theory is time independent and non-degenerate, and slowly we relax all these conditions. By that I mean the levels of H0 are taken to be non-degenerate. If they were degenerate, if two of the eigenvalues were equal, then you have to be very, very careful. By the way, yeah, in this particular case it will be totally trivial, but look at what happens. Something very different is going to happen. We had this correction with this infinite series and so on, but look at what happens if you set E1 equal to E2. So let us do that and ask what are the new eigenvalues. The character of the eigenvalues is going to change completely because now it is lambda minus E whole squared minus delta equal to delta squared. So lambda equal to E plus or minus delta, that is it. It is correct to all orders in delta. So this big infinite series just collapsed and you just got a plus and a minus. Incidentally, that again illustrates a general principle. We had a degenerate level here at E. I switched on this off diagonal perturbation and it split into two. There was an E plus delta and an E minus delta, taking delta to be positive. So it is as if this degeneracy got lifted by the perturbation and one of them went up and the other went down. That too will turn out to be a general feature. This too will happen in generality. This sort of thing is going to happen. But appreciate the fact that the moment these levels became degenerate, the nature of the solution became very different. There was not this infinite series in delta at all, it simply collapsed. That too may not happen all the time, but it is immediately evident that you have to redo perturbation theory. You have to redo this all over again.
That when you bring two atoms, the energy levels of each get split.
Yes, perturbations will always cause level repulsion, and that is what has happened. These two levels under the perturbation repel each other. That is again a general feature. Yes. So we have to put this in much greater generality than what we have done here. By the way, this problem also tells us, gives us a hint as to how to solve a general problem in which you have a pair of degenerate levels or more than one a level with some finite degeneracy. In the subspace of that degenerate level you have to redo the problem in this fashion, okay. So that is what is going to happen. Now let us put all this down in a formal way. So what are we going to assume? We are going to assume to start with, for simplicity, that this H0 is solvable, that it has a discrete spectrum. Later we must generalize this to a continuous spectrum, that is not very hard to do, and that these levels are all non-degenerate from each other. When you have a continuous spectrum you have to be careful because the levels are actually sitting on top of each other in a continuous band, so you have to go back and do it carefully. But to start with, let us assume it is a discrete spectrum and this H0 has a spectrum like this, not equally spaced, not necessary at all, some spectrum of this kind which has got energy levels of some kind, so that I assume that H0 has eigenfunctions phi and 0. I am going to put superscript 0 to denote the unperturbed portion of the problem, equal to some En 0 phi n 0. And this quantum number n labels these levels. So this is E ground state 0, this is E first excited state 0, E second excited state 0, and so on. Now I switch on the perturbation and ask what happens to these energy levels. If the perturbation is sufficiently small, in a sense which will become apparent as we go along, then I physically expect that this energy level will shift a little bit, up or down I do not know, but it is going to shift. So is this, so is this, and we have assumed, we are going to assume that this lambda, let us bring back lambda here, that is the conventional small parameter, this lambda is small, is the perturbation is such that this term, its matrix elements are going to be small in some definite sense compared to these energy splittings here. So that if this jiggles around a bit, this jiggles around a bit, etc., you can still identify the nth level. If this one came down here and this fellow went up there, then of course you have a very different problem altogether and you can't handle it with perturbation theory. But otherwise now we have got a very modest aim, which is to say these levels are still distinguishable and they get shifted a little bit, and the question is what is the shift, how much is the shift, and the states also would get shifted. There is no reason why phi n superscript 0 should be the eigenstate. So we assume that corresponding to this there is H on phi n equal to E n phi n. So we assume the same labeling is possible, except that En is not quite En0 but En0 plus some corrections, and phi n, this vector here, is not phi n0 in the state space but this vector plus some corrections, and the task is to find out what are these corrections. Now we are going to impose normalization, so I am going to assume that this forms a complete set of states in the space. So this original eigenfunctions form a complete set of states and form an orthonormal basis. So certainly I am going to assume that phi n 0 phi L 0 equal to delta n, they are orthonormalized. Now I try to find out what is phi n going to be. So what would be the general form for phi n? It is clear that if I focus on one particular state, so this is the nth energy level, dot 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 dot, this is the nth, this is E n here, and this was the original state, maybe the new state is here E naught, maybe the next state is here E1, maybe this guy is here E2 dot dot dot, and that is En. The unperturbed state was here, maybe the level was here, and that is the perturbed one. Okay. Now I would like to find out what it is in general. So the starting point is to say that based on our experience with this 2 by 2 simple kind of problem, in general if I fix a particular n and I am interested in finding out the correction here to this level n, so n is fixed here, then I can certainly write En as equal to En0, the unperturbed energy level, plus corrections to it which would depend on lambda, and I am going to assume that these corrections can be written in powers of lambda. We were going to question that assumption later, but we will take a look at, we will make this assumption to start with. So, and then I call the first order correction En1, I assume that this is true. So what is the meaning of this assumption? It says that this perturbation is such that it is analytic at lambda equal to 0, in the sense that the actual perturbed energy level is a power series in this small parameter lambda which converges inside some radius of convergence. That is the assumption. Therefore it starts lambda, lambda squared and so on. If you discovered the correction, first correction was proportional to square root of lambda, then this assumption is wrong, not true. But this is the simplest assumption that we are going to start with here. Then similarly I am going to assume that phi n is equal to phi n 0 plus a first order correction which is lambda times some other vector which I will call phi n 1 plus lambda squared phi n 2 plus dot dot dot, in general an infinite series.
So how can you be so sure that both times the lambda will be the correction factor? It can include something different also.
It could start with lambda cube, that is possible, it is certainly possible, but the assumption is certainly being made that with a linear lambda here, which means that H itself is analytic in this lambda, the assumption is the eigenvalues and eigenstates are also analytic. This
These E and states will shift by the same amount as H shifts.
H is an operator, H is an operator and it just shifts by a term which is proportional to lambda, but the energy levels could shift by amounts which have got all the terms in lambda, all powers, and similarly all powers here, the infinite number of powers. We saw that with the delta squared, square root and to the power half and so on. That does not terminate, that just goes all the way to all powers of delta.
What is this EN1, EN2?
Those are the corrections. So these are the coefficients of lambda, the coefficient of lambda squared, etc. I call first order correction, second order correction. So it was to keep track of that I put this lambda in there. Otherwise I could leave it here and say the superscript will tell me the order of the correction, but I want to constantly ask what order is it, how big is this term. So En1 will always appear with a lambda, so I know it is first order. These will not be functions of lambda, they are the numbers, they are coefficients.
H prime and EN.
They will depend on H prime. Yes, we have to discover what it is. We have to put this in and discover what it is. So the idea is to use this normalization. We are going to also normalize. We have to find normalized eigenfunctions. So we are also going to say phi n equal to 1. Just as the original thing was normalized, we would also like to normalize it. Actually we are going to have phi n phi l equal to delta nl, but right now I am focusing on just one of these states. So as well phi n is a normalized eigenfunction. With this input, now we have to consistently solve the problem. We have assumed that everything is a power series in lambda, absolutely convergent, which means if two power series are equated, you know you can equate term by term if they are absolutely convergent, and that is the whole point of successive approximations. You assume things are convergent in absolutely convergent power series, put a small parameter there and equate coefficients of like powers. That is all that is going to be done. Now you could ask, what is the rationale for it? How do we know this is going to happen? That you do not know in general. If these operators are crazy operators, you do not know it. For example, if H prime is a differential operator and you write everything in the position basis, for example, then there are theorems which tell you that if you have differential operators in which a parameter appears in an analytic fashion, then the eigenfunctions and eigenvalues are also analytic around lambda equal to 0. So you have theorems of that kind. Based on that, we are going to now use it and try to generalize it. Of course there will be notable spectacular exceptions and I will point them out as we go along, but right now let us assume things are alright, not pathological, and just ask what happens here. So I plug this expression and this expression into that, and what we get is H naught plus lambda H prime acting on phi n 0 plus lambda phi n 1 will work up to lambda squared plus dot dot. So let us work correct to order lambda squared just to see what happens, and you could, if you had enough energy, write down lambda cube, lambda 4 and so on, but we will see a pattern emerging. Okay. This is equal to En, but En is En0 plus lambda En1 plus lambda squared En2 plus etc., acting on the same thing. Plus dot dot dot, etc. And now we equate powers. Well, H naught on phi n 0 by definition is En0 on phi n 0. So the order lambda terms already match. This thing here is an input and that already matches, not surprisingly. The order lambda terms match immediately. The order lambda to the 0 terms match. Then we ask, what are the first order terms? We equate coefficients of lambda. So what we get is H naught acting on phi n1, that is this times that, and then there is a contribution which is H prime on phi n0. So plus H prime on phi n0, and those are the only order lambda terms on the left hand side, and that is equal to, there is En0 on phi n1. So let me call it H naught minus En0 acting on phi n1. So that takes care of this acting on that, and there is a term where this acts on that. So if I bring that to the left, plus H prime minus En1 acting on phi n0, this must be equal to 0. The coefficients of lambda on either side are equated. I bring everything to the left and this sum must be equal to 0 for consistency. Then look at the lambda squared terms. There is again an H naught, it acts on phi n2 out here, and that has got to be matched by an En0 acting on phi n2, and I bring it to the left. So it is H naught minus En0 acting on phi n2, then this term acting on this gives me an order lambda squared term, so plus H prime, but there is also an order lambda term coming from this lambda squared term coming from here, so it is H prime minus En1 acting on phi n1 and there is one more term which comes from En0 on phi n2, so that just stays as it is. Equal to 0. So we have taken care of all the lambda squared term order and so on. Now you begin to see the pattern. Yes, En2 acting on phi n0. Now you begin to see the pattern. H naught minus En0 appears here all the time, acts on the highest correction here, phi n1 here, and then phi n2 here and so on. Then H prime on the 1, the first order correction, acts on the immediately lower correction, phi n1, and then finally En0, the lowest here, acts on, oh this can't be En, this is En2, this term acting on that. So as the correction in the energy level goes to a higher order, what it acts on is of a lower order obviously, so that the powers of lambda match and so on. We write the entire series down this fashion, and if these series converge absolutely, then you have an infinite set of equations to find all the coefficients. So what is the task? The task is to find this number and so on, as well as this vector and so on. Please remember that these are vectors in Hilbert space. So there is no guarantee that this vector is parallel to that vector. It has other vectors in this Hilbert space pointing in other directions, of course. So this is the set of equations we have to solve. Now it is very easy to see, how to do this systematically, how to do this order by order. Obviously you do this first and then you do this and then you do this, you put the information from here in here and so on, because obviously if from this equation I can find phi n1 and En1, they act as inputs into this, etc. So what should I do here? I take this thing here, and the first obvious thing that comes to mind is take the scalar product of both sides with respect to phi n0. So if you did that, you get phi n0 acting on this guy plus h prime minus En1 equal to 0. Now what is this equal to? Well, you do not know what this does when it acts on phi n1, but you know what this does when it acts on this, and that is just En0, because it is just this equation and this is a real number. So if I take its adjoint, you get phi n0 bra with h0 acting on the right, from the right is En0 bra phi n0. So this term cancels out, this is 0, by definition this is 0, and this En1 is a number, therefore it comes out, and phi n0 is unity, it is normalized. So it gives us our first important result, which says, let us put that down here, it says phi n En1 is equal to phi n0 h prime phi n0. In other words, you give me the perturbation and I find the matrix element, the diagonal matrix element of this perturbation in the unperturbed basis, and that is the first order correction. So by definition this is equal to h prime nn, by definition it is the nth matrix element in the unperturbed basis. Remember I assume the Hamiltonian H0 is diagonalizable, I find its eigenvalues and eigenfunctions, then all these operators, all operators can be represented in this basis, in which, or the basis set is the set of eigenstates of H0. So in that basis this is the matrix element, the diagonal matrix element. So the first order correction was just the diagonal matrix element. By the way, recall that other earlier problem we did with an E1 E2 and a delta delta, the first correction that came was a delta squared, there was no delta correction at all, and the reason was the perturbation did not have any diagonal part. In the original basis the matrix became E1 delta delta E2 and there was no delta appearing in the diagonal elements, therefore there were no diagonal elements and that perturbation did not give a first order correction at all. That is why it started with a delta squared. So now we have this piece of very crucial piece of information, that you perturb a system and ask what is the perturbation of the nth energy level, then correct to first order, it is just the diagonal matrix element of the perturbation in this unperturbed basis. This question still remains, what is phi n1? We still need to find this, and what do we do for that? Well, certainly phi n1 can be written as a superposition of states in this Hilbert space, and the basis set we have chosen are the eigenstates of H naught. So I can certainly write this as a summation over L over all phi L zeros with some coefficients. These coefficients would depend on which energy level I am trying to correct, so that is going to depend on n, and of course it would involve also the summation index L. So in general I can write a thing like this, okay. And let us put that into this equation. If I do that, I need this equation, but I will come back to it. Write this down. So let me substitute for phi n1 the first order correction to this vector, which is an infinite series in the original basis. I plug that in there, and then I get a summation over L H naught minus En 0 on phi L 0 plus H prime minus En 1. By the way, En 1 I am going to treat as a known number. I already know this number, so let me just leave it here. H prime minus En 1 summation over L CNL phi, sorry, there is no summation here, En1, this number is known completely, this term is known completely. And what is my job? The task is to find, sorry, this is CL somewhere, right? Summation over L CNL. The task is to find the CNLs. What should I do? I take the scalar product on both sides with some member of the unperturbed basis, phi m for example. So I do phi m 0 on both sides of this guy. That phi m 0 is going to act on this H naught, is going to act on phi m 0, and what will it produce? Am 0. This is just a number, it is going to remain as it is. So this term will become Em 0 minus En 0, and then this phi m 0, there is a summation over L, by the way, sitting here everywhere. So summation over L C N L etc., and then it is going to be phi m 0 acting on phi with phi L 0 scalar product, which is a delta Lm, and because it is a delta Lm, this entire sum collapses and you are left with just CNM. So this term is CNM E m 0 minus En 0, that is it, because it is orthonormal. Delta phi m 0 phi L 0 gives you a Kronecker delta. I finish the summation and pick up just the m term here, plus phi m 0 H prime minus En 1 phi n 0. This is equal to 0. Now what is this going to give us? Well, this term H prime, the matrix element between m and n is just H prime mn. So this term here is plus H prime mn, nothing more than that, minus En1, which we already know, phi m 0 phi n 0 is delta mn. That is equal to 0. So we are in business. There are two things here. first is what happens if n is equal to m, the second is what happens if n is not equal to m. So it gives us a solution which says if n is not equal to L, n is not equal to m, well I wanted to put it in here directly, but anyway, if n is not equal to m, then this term is 0 and you get a formula which says Cnm is minus h prime mn over this guy here. So you immediately get Cnm equal to h prime mn over En0 minus Em0. I do not want this minus sign hanging around, so I just switch this guy in the denominator. What is it if m is equal to n? What is the diagonal portion? But what is the physical meaning of the diagonal portion? You see, you are trying to find the first order correction to phi n, and we already know that phi n is already phi n0 plus lambda times phi n1 plus higher order terms. This first order correction we are writing in this expansion, and the coefficients are what we are trying to find out. Now this state has to be normalized also. It is easy to see that this equation is not enough to determine C and n, because you put n equal to n, this vanishes, there is no way you can determine this coefficient. From this equation you can't find this coefficient, but you now take recourse to normalization. I would like this guy to be normalized order by order. So what is going to happen if there is a first order correction here and this was a 0 here? You can, without loss of consistency, take that overlap to be 0. In other words, if you insist on normalization and put some arbitrary Cnn here, you will discover that to correct to first order, when you normalize, it suffices to set Cnn equal to 0. That is the consistent way to normalize the state, and that is not surprising, because you see here is the original phi n 0, it is some vector in the Hilbert space, and now my statement is the correction to it might have a component along this to first order and in general in all transverse directions. And the statement I am making is that the first order term, if you want it to be normalized, there is no change in along this direction at all, but only normal to it, orthonormal to it. So with that proviso we can write this term down explicitly. Therefore if I put this in, by the way, Cnl is just Ln, and then this is just L. So I get a correction which says this formula together with phi n1 equal to summation over L not equal to n h prime Ln divided by En0 minus En0 acting on phi L0. So that determines for you the first order correction. And you can check that this function phi n0 plus lambda times phi n1 is also equal to 1 to first order in lambda. Of course this term here is going to, if I take phi n1 that is not equal to 0, there is a correction to order lambda squared, but that is going to be compensated by the lambda squared correction to phi n itself. So the whole idea is to keep normalizing correct to some order and pushing the problem further and further away. and then you get a consistent solution. So these are the first glimmerings, and I want you to step back a little bit and appreciate what is involved here. So the first order correction to this level, this was En0, that shifted a little bit. It could have shifted upwards, it could have shifted downwards, we do not know. That depends on the sign of this quantity here. Just the diagonal matrix element of the perturbation in the unperturbed basis. That is a very simple formula to remember. Then the first order correction to the state vector is phi n is phi n0 plus lambda times phi n1, and phi n1 has all these off diagonal elements. No diagonal elements appear here because L is not equal to n. This divided by this quantity here, which is called an energy denominator. Now you begin to see why this energy denominator cannot vanish. Then you have degenerate perturbation theory, you have to worry about it. So this thing here is explicitly summed over all L not equal to n. This side. Then what is the second order correction? Now we got to go back and ask, what does the second order correction look like? Well, one plugs in all this information into the second order equations and solves for En2 and phi n2 and so on. Let me just write down the answer for En2. This turns out to be, if I remember right, phi n0 h prime phi n1. It turns out to be the overlap of the matrix the matrix element between the unperturbed and the first order correction here. And what will this become? This is equal to, if I plug that in, it is equal to L not equal to n phi n0 h prime, and then I plug this in here. So it is equal to phi n0 h prime phi L0 and then h prime Ln divided by En0 minus El0. If I substitute this expansion in here, remember these are numbers, these are not operators, they are just matrix elements, they are numbers, complex numbers in general. Now what is this equal to? It is the matrix element of H prime in the unperturbed basis between n here and L here, therefore it is H prime NL, nothing more than that. So this is equal to summation L not equal to n H prime NL H prime Ln divided by En0 minus El0, and similarly a longer expression for phi n2 etc., which I leave you to work out. But you can simplify this a little bit. What is this equal to? These are both complex numbers. This is Hermitian. So if I took the complex conjugate of this, you get phi L on this side, phi n on that side, and H prime remains itself because it is equal to its Hermitian conjugate. Therefore I can write this as H prime NL modulus squared. So we have En equal to En0 plus lambda H prime N plus lambda squared summation L not equal to n H prime NL whole squared over this fashion goes on. So we have the second order correction as well. this is called an energy denominator. And it is clear for this to converge you are going to get more and more energy denominators, and this is now a reflection of what we had already seen in this simple example where we got an E1 minus E2 and you got a delta squared, and that is exactly what is happening here. So it is clear that the perturbation series has a chance of converging provided the matrix elements of this perturbation are small compared to the energy differences. That is the general rule under which you would have this kind, some hope of making this converge here. Now of course there could be special problems as we saw where this vanishes and it starts with this, and this could also vanish, it could start with the next term and so on, but one has a systematic perturbation expansion here. Notice something interesting. If I ask for the perturbation of the ground state of the system, then n is 0. I start with the perturbation of the ground state. Then in the ground state E00 is smaller than all the excited states, and the summation is over all the excited states, and this number is never negative and the denominator is negative. So it means the second order correction to the ground state is always negative, and like I said there are many problems in which the first order correction could be 0, and then you are guaranteed that the first correction will be negative, which means the ground state will go down rather than go up. That follows from this simple expression here. Okay. Let us try to apply this to a very simple problem, and this problem is just the harmonic oscillator with a perturbation added to it. And what is that problem, which is the so I start with the harmonic oscillator, which is p squared over 2m plus 1/2 m omega squared x squared, and this problem is solved. I know what the energy levels are, I know that En, and let me call it 0 equal to h cross omega into n plus 1/2. I am going to try to find corrections to this under a perturbation. So this is my H0 and my H1 equal to, or H is equal to H0 plus I add non-linear terms to this problem. So with an x squared potential I know how to solve it, but let us add x cubed, x4 or something like that. Suppose I add an x cubed, what is going to happen? So lambda x cubed. Well, one could sit down and do this problem explicitly, but you have to be a little careful. Let me ask, if I add an x cubed term, what do you think will happen to the ground state of the harmonic oscillator, which had an energy half h cross omega ground state? What do you think will happen if I add this with some positive number lambda? What do you think will be the first order correction? You have to find the matrix element of lambda x cubed in the ground state, and that is all you have to do. Physically, what do you think will happen? You have this feeling maybe this is going to become 0 because this potential was symmetric, it is a symmetric function, the ground state was a nice symmetric Gaussian, and now you say I want to find the matrix element of an odd function. What is the matrix element? After all, it is this thing here, this matrix element would correspond to calculating in our problem 0 x cubed 0. But if I wrote this in the position basis, then this stands for phi naught of x, which is a Gaussian e to the minus x squared over 2, that is a Gaussian, this is the complex conjugate of it, and so you have a product of two Gaussians e to the minus x squared, and that is multiplied by x cubed and integrated. You expect it to be 0, right? And indeed that will happen, because you see you can do this more easily as follows. X we know is a plus a dagger and then square root of what? in units of m omega over h cross, 2h cross, 2h cross, yes. Is this correct or do I have it the other way? H cross over 2 omega, right. H cross has dimensions ml squared t to the minus 1 and the m and t inverse cancel with the m omega downstairs, and so this is okay. Root of 2, so I have the proper commutation relation between A and A dagger should be 1, okay. So now I have to find therefore E0, that is the ground state, the first order correction. So E00 is equal to h cross omega over 2, that is the ground state energy, and I want to find E01 first order correction, first order in lambda. This must be equal to, by our formula there, it must be equal to 0 the perturbation x cubed in this problem, which is A plus A dagger cubed 0, and then h cross over 2 m omega to the power 3 halves. Now if I expand this, we know A on 0 is 0 and we know A dagger acting on the left on 0, on the brow 0 is again 0. Now that expansion is going to either have 3A cubed or A dagger cubed, all of which will give you 0 matrix elements, or 2 A's and 1 A dagger, and that is going to vanish. So it is clear that this first order correction is 0. The second order will not be 0 in general, etc. But this is a misleading problem, because if you draw the potential classically, what does this look like? What does the potential look like? It is an x squared term plus an x cubed. So it is clear that near the origin v of x as a function of x, near the origin is going to look like this, but sooner or later the x cubed term is going to take over. If lambda is positive, it is going to fall down, and then of course this goes up, and you are asking what is happening to the energy level here. It cannot be a stationary state because this will tunnel through out there and disappear if you wait long enough. So this is a symptom of the disease here. In this problem, although you can do this perturbation theory formally, the fact is our primary assumption that under the perturbation the set of bound states just shifted a little bit but remained bound states is no longer true. So in fact this perturbation series cannot converge absolutely. You could write it down, it could be an asymptotic series or something like that, but if you work out all the terms, it cannot be an absolutely convergent series with any finite radius of curvature. However, it will give you the shift in energy because they form what are called metastable states. If the parameters are such that the tunneling time is very long, then the tunneling probability is small, it will give an approximation to the energy. So this was not so great an idea, but what happens if I do this x4, then you are in shape, because now presumably the potential looks still parabolic here, but it becomes a little steeper than parabolic for sufficiently large x because the x4 takes over. Now you can see that classically all the motion is always periodic orbits. Quantum mechanically it will be a discrete spectrum in this problem, rigorously a discrete spectrum. Then we could ask what is the correction going to look like. Now you have this, x is this, so now this is to the power 4 and that is squared. What happens now? How are you going to compute this number? Pardon me? So what I have to do is to take this a plus a dagger to the 4 and actually write it out. There is going to be a huge number of terms. This is what I want to compute, and please remember that a on 0 is 0, 0 on a dagger is 0 because it is the ground state. If I expand this out, the a to the power 4 term, the first term is obviously going to give me a 0, it is going to disappear. Similarly, the a dagger to the 4 is going to give me a 0. Then there are terms in which there are 3 a's and a single a dagger, and that term is obviously going to be 0. And similarly 3 a daggers and a single a is also going to be 0. The only terms that will contribute are those in which you have a like number of powers of a and powers of a dagger. And how do you compute this? Well, you have to sit down and write this thing out explicitly, fully, but let us see if there is a cheaper way of doing this. A plus a dagger squared, in this problem there is, because this is equal to a squared plus a dagger plus a dagger a plus a dagger squared. Okay. Now that is equal to a squared plus a dagger squared plus, you can write this in a simpler fashion. What should you do? You should try to bring all the a's to the right hand side, because a acting on 0 will give you 0. So you should do what is called normal ordering. In other words, take all the a's to the right, take all the a daggers to the left, and then use the fact that a on the vacuum is 0 on both sides. So what are the terms that are going to contribute here? There is going to be a term which is a squared so what I want is the 4th power of this plus a dagger is a dagger a plus 1, but a dagger a is a number operator, right. So this is 2n plus 1, where n is the number operator. The number operator acting on the vacuum is 0, right. So that is a cheap thing to do. So this to the power 4 gives me this to the power 4, gives me this squared. Pardon me? Sorry, this is and I have to square this guy here. So what is going to survive? What is going to survive is a term a squared a dagger squared. The a dagger squared a squared term will vanish, and then this squared is going to survive. 1 when I do 0 here and 0 here on this side. Okay. This term in itself again can be written as a dagger, and you bring the a dagger to the left once again and write it in terms of number operators. You are going to get a contribution 2 from here and a 1 from here, so the whole answer is going to be just a 3, and all other terms vanish. So this is the trick, try to normal order such products, put all the a's to the right, all the a daggers to the left, and then when acting on the ground state it gives you 0. Whatever survives, whatever numbers survive will be the only contributing factors. So in this problem it will turn out that this thing here is equal to 3 times the first order correction. So does it go up or down? Does half h cross omega go up or down? Goes up, it is the first order correction. The second order correction is guaranteed to go down, but if lambda is sufficiently small, that will be negligible compared to the lambda correction, okay. And so on. You can compute all the higher order corrections to it. That would be a very good approximation, which you could do this problem numerically to the exact eigenvalues. One final point, just to deflate the whole thing. Do you think that this perturbation series is absolutely convergent with a lambda x4? This is a very tricky issue, it is not simple at all, and the answer is it cannot be an absolutely convergent series, and the reason is very interesting. If this is true and the series converges absolutely, right, then it means that the power series that you get have a finite radius of convergence about lambda equal to 0. So everything is supposed to be analytic about lambda equal to 0. In other words, the problem should be unchanged in essence even if lambda is negative. The Hamiltonian should be Hermitian, so I can't make lambda complex, I can make it positive or negative, but if I make lambda negative, what happens to that potential? If lambda is negative, this is for lambda greater than 0, lambda less than 0, it is still parabolic out here, but sooner or later the negative lambda will take over and the potential will go. So the ground state that you get here or any of these excited states would also be metastable states. That problem technically does not have only bound states for negative lambda, and yet that is the assumption that the perturbation is analytic in lambda and therefore makes sense as long as the Hamiltonian remains Hermitian. So this is a technical point and much work has been done on trying to make sense out of this perturbation series, but it does not diminish from the fact that this perturbation series will give you very good numerical values, and this is very typical of what happens in asymptotic series. Numerical values will be very accurate, but technically the series itself may be formally divergent, okay, and so things of that kind start happening here. I do not want to get into that, but this tells you a little bit about how non-degenerate time independent perturbation theory functions. The crucial results for our purposes are that the first order correction is the diagonal matrix element of the perturbation, and the second order correction is the off diagonal elements mod squared divided by the energy denominator, okay, with the corresponding expression for the wave function. And notice that even in the first order correction in the wave function in the state vector, this these energy denominators appear out here. So in the second order correction you would expect a product of two such energy denominators and so on. So this is the way the perturbation series is developed. The next task which I am going to do next is ask what happens if you have degeneracy, and finally we will look at what happens if you have a time dependent perturbation and then look at its simple applications, okay. So let me stop here today.